Hi, everyone. We're going to jump right in with kind of a messy example to introduce this new idea, but I promise that my next example will be a little bit simpler one, just so that you can really make sure you've got the main idea. But I wanted to start with an application so you can really see what's going on and that this is a useful thing. So we're going to spend a good part of this quarter learning about different functions that have different shapes. Right now, all we've got is lines. So we're going to look at something like this graph that we're given, and we're going to say, okay, interesting shape. It kind of looks like I could make it up with several straight line pieces, and that's what the red dashed lines are for. So this is data on the temperature in kelvins at various heights in a single location. So you park at a single location on Earth, however they're testing this drone or something, they send up and they check at all these temperatures going up pretty high, 0 to 5,000 meters, to see what the temperature is doing. And we get this cool picture below, and we see that there's some kind of dramatic changes in what's happening. It starts off with a fairly steep slope here, and the temperatures are rising, rising, rising. And then before too long, you pretty quickly level off a lot. So there's sort of a break happening. My pen working right about here, where the behavior changes, and the blue is the actual data points. You can see it's kind of rounded off. We can't capture that with straight lines. We will be able to with some of our other functions. But for now, that first straight line piece looks like it does a beautiful job right before the leveling off happens. And then after the leveling off happens, the second line piece also seems to be doing a pretty good job until we get to somewhere around, I don't know, like 3,200 meters. And then it gets a little steeper again, and our data cuts off right about that 5,000 mark. So what I want to visualize is splitting this into 3 parts. So the first part is pretty skinny. I'm going to call that phase 1, piece 1. The second part starts right where phase 1 ends, and ends a little after 3,000. And then the third part starts a little after 3,000, ends right about 5,000. So what we want to do is just try and find the equation for each piece of this line. So I'm going to color code a little bit. So piece 1, we're going to do in red, matches the dash line we already had, so that's not very pretty. But what we want to do is try and find an equation for the line that seems to be doing a pretty good job of fitting the trend there. So I'm going to try and estimate a couple of points. And one nice thing happening is that this point right here appears to be a y-intercept that really is at 0 on the horizontal axis, which is representing height. So I'm going to call that h. And then temperatures on the vertical axis, I'm going to go ahead and call that T. So 0, and then we have to estimate a little. It's definitely above the 287.5 line. The little white grid lines that are going across are about 2.5 units apart, 2.5 kelvins. So I'm going to say that's maybe like half Kelvin from the bottom. We're going to say that's roughly 0. I don't know why I'm putting it there. I started it down below. 0 to 88. So try to be careful, but you are estimating, and don't get too nervous about that. And then on this end, it looks like we've gone over what to about here, really. I drew my gray line a little far over. So this is 1,000. Halfway there would be 500. It looks a little less than a quarter of the way there. So I'm going to say that's about 200. And then we're a little below that 297.5 mark, so maybe that's about 297. And I'm not trying to force these to be nice integers, so don't be shy about keeping a decimal point in there if you think that that's what you need. Maybe you think that that's 297.2 or something like that. That's fantastic. Okay, so equation for a line. This one's nice. I'm given a y-intercept, but I do still need a slope. So let's go ahead and calculate that. So this is for piece number 1. I'm going to take the 297 minus the 288, and then I'm just going to be really careful to keep that same order. 200 was the x value that went with 297, and then it's minus 0, so that works out kind of nicely. Okay, so 88 to 97, that's 9 over 200. Okay, so let's check out what that gives me. 9 over 200 is 0.045. So pretty flat slope, and if you pay attention to the scale on your graph, that seems right. The vertical tick marks are 2.5, the horizontal tick marks are 1,000. So this is definitely getting exaggerated to look a lot more dramatic in the y direction than it is. Okay, and then this one, I can just put it together now. So I'm just going to call it T1, temperature piece number 1 for now, but my plan is to put this all together into a single function, teach you some new notation. So slope of 0.045 times h and a y-intercept of 288. Okay, so there's piece number 1. Piece number 2, I'm going to use blue if you can see that. It's going to be that line segment. So it shares this same point 200, 297. And then on this end, what do we have? Maybe 3,200? 3,200. And then the y value on that, we're a little below 300. So that's maybe 299.5. So for piece number 2, same process. We need to find a slope. So I'm going to take that 299.5, and we're going to subtract the 297 that was our second point last time. And then 3,200 goes with 299.5. And then we're subtracting off 200. Okay, so our y value has gone up by 2.5, and our x value has gone up by 3,000. So even smaller slope, which makes sense. This is a really flat looking piece of this graph. So 2.5 over 3,000 is, how many zeros? 3 zeros, 0, 0, 0, 8, 3. And then the 3's keep repeating, but that's a pretty good approximation right there. When you have those tiny numbers, don't chop them off at 2 decimal places. Try and get out there to get some actual information for me. And then this time we don't have a y-intercept, so I'm going to go ahead and do a point slope form, and I'm going to use that point 200, 297. So I'll call this piece T number 2, temperature piece number 2. And we need to subtract the y value, minus 297. And then we need our slope. And then h minus the h value, 200. Okay, so this is our setup. And then it's just a little bit of rearranging. So we'll want to distribute, and we'll also want to add the 297 over here. Okay, so 0.00083 h, and then if I take that same number and multiply it by 200, negative 200 even, and then we're going to add 297, I get 296.83. Okay, so there's piece number 2. If you're getting bored of watching me do this, now would be a great time to try and find the equation for piece number 3 on your own, and then tune back in to see how we tie these all into a single equation. So my point here looks like it's at 5,000, and then it's a little bit below 307.5, so we'll say maybe about 307. So let's start right below the graph. So my slope, I'm going to take that 307. I'm going to subtract the 299.5, and then I'm going to match my x values. So the 5,000 goes with the 307, and the 3,200 goes with the 299.5. Okay, so my y value went up by 7.5. And my x value went up by, 1,800, not quite 2,000. Really wish my pen would write more smoothly. 1,800. Okay, so I got a little bit of round off here again, so approximately 004. So my start for this would be, okay, this is piece number 3. So T3 is going to be subtract the y value. Which point do I want to use? Let's use the new point, 307. Don't get any more decimals in the mix than we have to. And then the slope, h minus 5,000. Okay, so we're going to have T3. Go away. T3 equals, I swear I'm not bumping them anymore, equals 0.004h. Okay, there we go. And then we need to multiply the 004 by 5,000. So we're going to get 20.83, and that's minus. And then we're adding the 307. Okay, so when we put that together, we get piece number 3. Okay, T3 equals 0.004h plus 307, 286.17. Okay, so here's the new and really important part. There is a way to join all 3 of those equations together to make a single function, because this is a single problem that we're trying to write equations for. We don't really want 3 separate equations. We want to say this is the function that plugs in the height and outputs the temperature. So it's really just a bit of notation, and it looks really scary at first, but it's really sensible notation when you get used to it. So I'm just going to call my function t of h. So this incorporates all information about temperature and height. And I am going to show that my function is made up of a few different pieces by using one big squiggly bracket to join them. And then you just list your pieces one below the other. Generally, we go, like thinking of the graph, we would go left to right. It would still work if you didn't, but that's what I'm going to try and do. That makes the most sense usually. So the first piece, the far left, is 0.045h plus 288. The next piece, the middle piece, is 0.00083h plus 296.83, and then the last piece is 0.004h plus 286.17. And this is a pretty good start, but it does have a problem. The problem is, without looking at the graph and knowing the process that I went through, I would have no idea if I came to this big formula when to use the first equation, the second equation, or the third equation. So a really, really crucial part of this notation is giving a domain restriction to each piece to tell us when to use it. So we generally just put a comma, or you can write the word if in there if you prefer one of those two. And then we just write when this part of the formula is valid. So the far left piece was valid for h's between 0 and 200. So we're going to say if 0 less than or equal to h less than or equal to 200, we use the first piece. The second piece went from 200 to 3200. 200 to 3200. And there's a choice that you get to make here about which one gets an equal to and which one doesn't. So for the 200, notice I included the 200 for the top piece of the equation and then excluded it for the middle piece. You could flip-flop that. It doesn't matter. What does matter is that you shouldn't include 200 for both, because then you don't know which piece of the equation which equation to use. And if you exclude 200 for both, then technically you aren't supposed to use any of the pieces. So pick one, it doesn't really matter which. And the same is true for the 3200. I decided to include it for the middle piece, which means when I start the the third piece that goes from 3200 to 5000, I'm going to exclude it. I do want to include the 5,000 for sure, because there's only one piece that could go with, and the 0 for sure. But otherwise, you get to pick and choose which piece uses the is used for 200 and which piece is used for 3,200. Okay, so it's tricky notation. I will show you a simpler example, but I'm going to have you dive in and try one that's in context and has kind of messy numbers before we do that as well. So I hope that's making sense. Thanks for watching.